So it's my great pleasure and privilege to be here, have a chance to honor the great man Michel at this sort of turning point in the middle of his career. And I hope the next 60 years are even better. So everything I want to talk about today is joint work with Alden Walker. And for more details, or even some details, the papers on the archive at this archive 1304-2188. So I realize it's late in the day and people here have got very different backgrounds. We have people sort of from different areas of topology and group theory and dynamics and so on and so forth. So I want to keep things very concrete in this talk, and so I've sort of prepared an executive summary. And so I'll make these very precise statements in a minute, but the sort of the overview is I want to think of it in the following terms. First of all, most groups, I want to argue, contain surface subgroups. Here, groups are going to be finitely presented groups, so most finitely presented groups, in some sense, I'm going to argue contain surface subgroups, meaning subgroups isomorphic to the fundamental group of a closed surface of genus at least 2, and usually pretty big genus. Second of all, the surface subgroups are not sort of hiding. They're very nicely embedded. The geometry of the embedding is as sort of close on the large scale to sort of isometric as it could possibly be. These subgroups are 1 plus epsilon quasi-isometrically embedded in the big groups. And third of all, something which is sort of practical importance to me and maybe is part of the way in which this is related to the method of proof. The surfaces are in fact very easy to find and to certify, meaning you can really just, someone gives you a presentation, well, and you have a computer, you can in fact find these surfaces in a practical way and certify them to be injective under reasonable circumstances, and even with particular interesting sort of challenge examples. So, all right, so what do I mean by most groups here? Well, I'm really talking about a sort of a model of random groups proposed by Gromov, but there's several different random models that the theorem sort of applies to, and I'll sort of describe one of them and also mention a little bit what how much flexibility there is in the construction. So the idea is, so what do I mean by most groups here? So a group here, I'm thinking of these really as most presentations of groups. And the presentation doesn't determine the group, but actually most presentations, the presentation determines the group. And so I'm not going to pay too much distinction between, I'm going to make too much distinction between presentations of groups and the underlying abstract groups themselves. So the idea is that we have a group here, we have a finite generating set. So this is, okay, so the random groups model due to Gromov. So you fix some free group of rank at least 2, finite. These are going to be the generators. And you fix the generators. Okay? And then you've got a group which is given by, well, these generators together with a bunch of relations. And so the random groups model is sort of a model for a kind of a law for how to choose the relations. And there's a couple of parameters in the model. So the first thing is to say, well, how long would you like the relators to be? So if you sort of want to say, look at relators of length n, so in a free group of rank k with a free generating set, there are approximately 2k minus 1 to the n reduced words of length n And I'm not really going to distinguish in this talk between reduced words and cyclically reduced words. It makes a difference, but in the kind of estimates that I'm going to end up using, they're not sensitive to such differences. So either sense, these could be reduced words of length n, or you could insist on them being cyclically reduced words of length n if that's your thing. And if you don't want them to be exactly length n, the length can vary a little bit if you want. And you can even have all different kinds of laws for the relationships of the different lengths. But there's about 2k minus 1 to the n reduced words of length n, and you want to choose some subset of them and throw them in as relators. And so what Gromov proposes is a good way to choose them, is to sort of fix a kind of a density, what fraction of the words you're going to add. But the trick is it's sort of a logarithmic density, right? So you sort of fix a density d, which I guess is going to be less than 1, and you throw in 2k minus 1 to the power of nd random independent reduced or cyclically reduced words of length n as relators. Yeah, right. Okay. So this is sort of the model, and so this is kind of turns out to have some interesting properties. So Gromov sort of first proposed this model and proved a few interesting things about it. And one of the most fascinating aspects of it, in fact, is the existence of a kind of a phase transition. So Gromov showed at density, and so then I should say, so there's two parameters in the model. So what one likes to do is to sort of fix first a density d, and then let n vary. So for a fixed density d, you look at a collection of 2k minus 1 to the nd random independently reduced words of length n in the fixed generating set for some particular n, and you get a group, and it has, or you get a law on groups. You get a particular sort of some random collection of groups, but a finite collection of groups. Some of them have some properties, other ones have other properties. And you say that a property of a random group at density d holds with overwhelming probability, or with probability going to 1 as n goes to infinity, if this property holds with overwhelming probability as the length n goes to infinity. So you want to find a property. So the idea is d is fixed, but n is going to be very large as necessary for whatever kind of arguments you're using to kick in. Okay, so large here in theoretical terms means that the log of n has to be large. So if the log of n is large, n is going to be quite large. But what's sort of interesting is that one can sort of do experiments when n is merely actually pretty small, 60, 70, something like that. And there, in fact, we can see that the phenomena in practice actually start to kick in at that scale, and we can construct surface subgroups easily, certifiably, and so on with high probability. No, and you might, actually. So let me tell you what Gromov showed. Gromov showed, firstly, at d bigger than a half, with overwhelming probability, I'm not going to write that, but the group G is either the trivial group or Z mod 2Z. All right? He also showed at d less than a half, G is infinite, word hyperbolic, non-elementary, and in fact two-dimensional, by which I mean that there's a finite 2 complex whose fundamental group is G, whose universal cover is contractible. And you ask which finite 2 complex. In fact, a presentation like this determines a 2 complex in a kind of an obvious way. We take a bunch of circles or rows for the generators, and we attach disks, one for each relation, and we get a 2 complex. It's well-defined up to homotopy, or if we kind of take simplicial maps, it's sort of well-defined 2 complex. And this 2 complex turns out to be aspherical. Okay? Yeah. I mean, for example. Yeah. And then 3, so this is Gromov 1 and 2. This is a very nice theorem of Damani, Girardel, and I can't write it and say it at the same time. In fact, I can't even write it. Chatitsky, they show also at density less than a half, the group is one-ended. And its boundary is homeomorphic to the Menger sponge, or whatever it is, sort of universal one-dimensional compact guy. So these are sort of extremely non-trivial groups, but at a very sharp kind of threshold. And the idea is that if I have some number of pigeonholes, and I pick, you know, if I have n pigeonholes and I pick n plus 1, I put n plus 1 pigeons in them, then I'm forced to have a match. But if I sort of put the pigeons in at random, I only need sort of square root of n pigeons, because then I have sort of n pairs of pigeons to get a match. And so if you kind of have density bigger than a half, you're extremely likely to have, say, the same relation. At least one relation will appear twice. And if one relation is going to appear twice, well, then probably one relation will appear, and then another relation will appear which differs from that, say, in exactly one letter. And then what that means is that, you know, one of the generators is equal to another generator, and that'll happen a finite number of times and show that each generator is either equal to every other generator and either trivial or has equal to its inverse. So sort of a parity thing might kind of kick in. So that's why at density above a half, this sort of holds. That's basically the argument. The reason that this holds is essentially kind of a small cancellation argument, and I don't want to go into the details of it, except to say that some aspects of the sort of small cancellation theory were developed in much more detail by Jan Olivier, and it's some of his tools that we end up using a little bit later on. Okay, so now, so at density less than a half, we get these hyperbolic groups. So most groups are hyperbolic, if this is your idea of a typical group, finitely presented group. And so what we prove is that, so I'm going to write, it's a little bit cheeky, at any density I'll put an asterisk here, d between 0 and a half, I'll just say a random group at density d contains, I'll just say, many 1 plus epsilon quasi-geodesically embedded, quasi-isometrically embedded surface subgroups. I mean, technically, you need to tell me epsilon before I tell you how big the length of the words need to be. But as I said, in practice, they don't end up needing to be too big. And obviously, you need some kind of control, because I can't even tell you the group's hyperbolic, or, you know.
What do you mean by d greater or equal than 0 star?
Yes, well, so that the star means that I'm going to explain this in a second. There's another model of a random group, which is called the few relators model, which Richard sort of talked about in a way earlier on in the week. So there's also, so the few relators model. So this is a different sort of model where we just sort of fix some number n constant and little k, and we let G have k generators and capital N relators. The point is that the number of relators is fixed. It's not getting bigger as the length of the words get bigger. And so let's let n, capital N, be at least 1. Otherwise, it's pretty hard to find a surface subgroup. And then this is what I mean by density 0 star. I mean the few relators model, excuse me. I mean the few relators model. If you fix a finite bigger than 0 number of relators and you pick that many relators, and if they're long enough, with very high probability there will be lots of 1 plus epsilon quasi-isometrically embedded surface subgroups. And in fact, the argument, the method of proof is kind of interesting because, well, how do you get a random group at density d? How do you generate a list of relations which are independent, randomly sampled? Well, what you can do is you can generate them one by one. I first decide what the first relation is. Then I pick another relation at random. I add that. I pick another relation at random. I pick that. And I keep adding them one by one. So you can think of a random group at some density as actually a sequence of groups obtained by just throwing in these relators one by one. And what we do, in fact, is we show that if we just look at, say, a one-relator group, a random one-relator group, we find a surface subgroup there with high probability. And then we show that as you throw in all the other relators, the surface subgroup just stays essential and geometrically very nice with high probability. So the surfaces, you might imagine a circumstance where the higher the density was, maybe there'd be more and more surfaces, but fewer and fewer of them would be injective. Actually, and I think that's sort of true morally, but in fact there are some surfaces you can find right at the start that persist all the way to the end. So there's kind of quite a bit of flexibility here. There's a few other kind of bells and whistles you can do here. This doesn't go up much higher. So all right. So let me sort of want to leave the theorem up. So a few remarks. So one, if the density is strictly positive, and I guess I do mean less than a half, but yeah, so if the density is strictly positive, we can choose these surfaces to be homologically essential. In G. So second of all, the genus of the surfaces. What does what mean? Okay, so if you have a closed-oriented surface, then in dimension 2, the homology is Z. And so a map from a surface group to any other group induces a map on homology, two-dimensional homology of the group, to two-dimensional homology of the target. And the image of the fundamental class in the target is non-trivial. So the point is there's a two-dimensional homology class in G represented by an injective surface subgroup. Yeah, exactly.
So you're taking non-trivial rational coefficients? I mean, infinite order?
Yeah, yes. Okay, so that's homologically essential over Q. Sure. The genus of the surfaces at length n, so it's going to depend on n, can be taken to be of order n. And actually, I think one can do little o of n, but let's just to be safe, let's just not ask whether I drew a big or a little o. And you could ask, is this the smallest genus of an essential surface? And actually, we conjecture. So we conjecture that the smallest genus essential surfaces have genus n over log n. And what we can show is that actually most And again, rational, well, I want to say, let me just say you can find homologically essential surfaces, and again this is homologically essential over Q of genus O over n over log n, and this is sharp, and we can even sort of say what the constant is roughly. So the third thing to say,
Was that stronger than what you wrote up above then?
what did I say?
You said the genus was
Well, these guys here, we can choose surfaces to be, yes, all right, I guess I should say
the first line.
essential and. Essential means here pi1 injective.
No, I was looking at the first line on the first line of assertion 2 there. It says the genus can be taken to be O of n.
These are of these essential surfaces. So yeah, I'm using the word essential, I guess, in two standard but confusing ways. A surface could be essential, meaning it's pi1 injective, and it can be homologically essential, meaning it represents something non-trivial in rational homology.
Oh, I see. So when you find these homologically essential things of genus O of n over log n, those may not be essential.
They may not be essential. We conjecture that some of them are, yes.
So my three-manifold intuition fails here, right?
Well,
Can be essential.
this is actually, I hope your three-manifold intuition succeeds. And I guess this is a question that, as far as I know, this is an open question. I think it's a really terrific question. Supposing I have a hyperbolic group, supposing I have a two-dimensional rational homology class, well, it's represented by maps of surfaces, and you can try to find a map of surface which projectively represents that homology class. It's only rational. You might have to take a multiple of it. And you could ask, is there a map of a surface which is norm minimizing in its projective class? If there is such a surface, actually it's necessarily pi1 injective. This is follows by, you know, Lerf for surface groups. But there may not be a guy minimizing, because you might have to just go to higher and higher degrees to get closer and closer projectively to the norm. So conjecture, actually there is always a norm minimizing surface in a rational homology class. Might be empty if the homology class is 0. It might not tell you anything. Then such a thing would be an essential surface. I don't know if it's true or not, but I think that's a good conjecture, and even if it's false, I think that's a good problem to try to prove, or something to try to prove or not. The third thing I wanted to sort of say is that the very fact that these surfaces are quasi-isometrically embedded is what lets us know that they're essential. It's sort of, these are constructed using probability, but certified using geometry. It's the nice thing about 1 plus epsilon quasi-isometrically embedded is that it's a local property. If you're building something, it's much easier to certify that something has a locally certified property. What would be much harder to do is to find a surface which was essential but not quasi-isometrically embedded. And I think this is another very good question. What are the class of hyperbolic groups that contain essential surface subgroups which are not quasi-isometrically embedded? By a goal, we now know closed hyperbolic three-manifolds groups have this property. I don't know. So the third sort of remark I want to say is that you might object that this definition of random is sort of biased to choose relators that are incredibly symmetric in a certain sense, which is a bit silly because it really depended on a choice of generators, and maybe it's not natural or something like that. Let me just sort of say that you can certainly soup this up in many ways. Supposing you have a favorite letter. My favorite letter is B. B could be one of your generators, and you want to produce random relators where, you know, you like B a lot. So when we get a chance, you throw in a B, and you tend to favor the Bs and don't care so much for the Cs and Ds. And then you can sort of produce random words according to this law. So you have to be a little bit careful now. A random word of length n, well, there's still the same number of them, but they're kind of biased in a different way. And the right way to count is not by how many there are, but somehow by the entropy. So there's sort of an entropy of this process. And let's let lambda, or I guess log of lambda be the entropy, one wants to look at add lambda to the nd relators. So let me just, yeah, so this is random group where the words are produced by, let's say, a stationary Markov chain, stationary finite Markov chain with entropy log lambda, so that these groups at density or more than, lambda to the n times a half, these are trivial and less. Oh, sorry. Okay. So the density d means lambda to the nd words. But density d means lambda to the nd random words, random independent words. And then, again, for d less than half, bigger than 0 star, you're going to contain surface subgroups with the same sort of estimates, blah, blah, blah. OK, so that's sort of the statement of the theorem. I sort of wanted to be clear about that before I started. Are there any questions about this before I say something about some of the ingredients in the proof?
In this third model, the results of Gromov still hold?
Yeah, yeah. And there are other things you can do, right? You could start with a hyperbolic group as a seed instead of a free group. There, things are much more subtle. If there's torsion, certain kind of torsion, there's this, Jan Olivier discovered this, bad words, bad torsion words that can cause things to collapse too early. But anyway, at some density in that model, things are fine. Yeah. Anyway, so this is the arguments that these people prove all work in this sort of slightly more refined model. Yeah. I mean, you have to be a little bit careful. A stationary Markov chain could just have the letter B over and over. That obviously wouldn't be, yeah, that's great, but not the model we want. You have to have some kind of hypotheses. All right, so I want to say there's sort of an ingredient. There's two ingredients to the argument, but one of them I think is kind of, it's just sort of, in a way, it's kind of a combinatorial argument, which is, I think, of independent interest. And I want to at least sort of state it carefully and say what some of the ingredients are. So where do these surfaces come from? So the methods are really just sort of small cancellation methods, diagrammatic methods, and I actually meant to keep this. So I have, here's my group. It's pi1 of this space. And I have a surface mapping in. That's the same thing as a surface group mapping to this group, because as I said, this is a k pi1. And so I kind of have the surface. I imagine it's got some sort of, it's a simplicial complex. It's got, or not simplicial complex, it's sort of a CW complex. It's got a sort of one skeleton mapping to this one skeleton here, and two skeleton mapping to these sort of pieces here. And let's just start with one relator. So we've got a single relator R. And so what we're trying to do is to build a surface in the following way. Well, if we ignored the relator, what do we have here? We've just got a graph. And if we take the two cells away from this surface, we also have a graph, but the graph has a bit more structure. It remembers how it sat in a surface. So it's a fat graph. So it's a graph together with kind of a thickening to a surface. Right? So this is the fat graph, which is the core, which is a thickened one skeleton of this surface, this hypothetical surface we want to construct. So the way we do it is we build the fat graph, then we glue on copies of this disk, and then tautologically this surface comes with a map to this complex, which, by the way it's built, will turn out to be pi1 injective. Okay? So what do we know about this fat graph? So this fat graph, so what is a fat graph? So a fat graph is just a graph, finite graph. Each vertex, there's a circular order on the edges incident to it. So it tells you how to fatten it up locally to sort of think of it sitting in the sky, as a sort of spine of a surface. And so each edge of this fat graph is just going to map, say, to an edge here, a generator. And so if we kind of think of this as a graph sitting in an oriented surface, the orientation is going to put an orientation on the boundary edges, which is kind of disagrees on opposite sides. This picture is terrible, so let me draw a little bit bigger, a little piece of it. Here's a bit of the fat graph. So here's the spine of it sort of sitting in here, and you kind of have, this is the orientation on the boundary. So here's the surface. Here's the fattened fat graph. Okay? And so what do you have? You have these sort of oriented curves, which are the boundary of the fat graph, and if you decide where these edges go over there, then what you have here, you read this off, you get a cyclically reduced word, or anyway, a cyclic word in your generators and their inverses, and that's going to be capped off by sticking in copies of R or R inverse. So what do we need to do? We need to take a collection of cyclic words, a bunch of copies of R and R inverse, and we need to sort of arrange them in some clever way as the boundary of a fat graph. And then if we can do that, we can cap them off with disks. We get a surface. The surface maps to our group, and we hope we have an injective surface. Okay, so the key is that the fat graphs we build are thin. So it's the thin fat graph theorem. All right. So let me just sort of say, emphasize what I have here. I have this sort of fat graph Y, and I imagine fattening a fat graph means applying some operation to it which builds a surface with boundary. So this is to fatten a fat graph. Then you take its boundary, and this boundary is a bunch of conjugacy classes in FK, reduced cyclic words in FK. Okay, and the idea is to go backwards, given a bunch of conjugacy classes in FK, to arrange them as the boundary of a fattened fat graph. So the thin fat graph theorem says the following. It says, well, I'll state it, then I'll explain what it means. So there's a couple of parameters. You first pick a big number L, and you need L to be very big. Then you pick a much bigger number T. Then you pick a number epsilon which is much smaller than 1 over T. And you can make these more effective, but anyway, let's just say much, much smaller and much bigger. So what do we have? We've got a collection of words. We've got gamma is going to be a collection of, let's say, cyclically reduced words in FK, so a bunch of conjugacy classes. It might just be, you know, the same word over and over, or the same word in its inverse over and over. And in order for this collection of words to bound a surface, the homology class in the free group it represents has to be 0. So we want it to be a homologically trivial collection of cyclically reduced words. Homologically trivial, meaning in H1 of Fk. That doesn't mean that the individual words are homologically trivial, but that the sort of the formal sum of them is homologically trivial. So we've got a bunch of loops which, homologically speaking at least, could bound a surface in the free group. And they satisfy a kind of equidistribution property. And I want to say that such that the components, and there might be lots of components, the components gamma I of gamma are all sufficiently random on a sufficiently big scale. So I'm just going to quantify that by saying T epsilon pseudo-random. And all I mean is that on a scale T, if I look at the subwords of length T, they are distributed in the way you'd expect in a random word up to an error which is controlled by epsilon. Okay? So it's just some idea of being equidistributed enough on a certain scale, far from actual randomness. It's a much more mundane property, much weaker property than actual randomness, but this kind of pseudo-randomness then gamma is the boundary of the fattening of a fat graph y, where y is a trivalent graph such that every edge has length at least L. Okay, so y is a trivalent graph. It's not very bushy at all. Not only that, but it's a long time between junctions, long straight stretches. So this fat graph, it's got a few places that bulge out, but basically most of it just looks like extremely long, thin rectangles. It's a very thin fat graph.
You choose this family. You're supposing it's cohomologically trivial. That means they covariant some surface.
Yep.
And then
Yep.
the fat graph is going to define another surface which you glue to the boundary. Get a map of the closed surface. Is that
No. In order for there to be a fat graph whose boundary of the thickening is gamma at all, I need to be homologically trivial. That hypothesis is just there to ensure.
Okay, but
Yes.
but this is just so far. This is just giving you a map of a bounded surface then into the.
Yes, I've got a fat graph.
And you're going to make these things the relators is the point at the end of the day. They're going to be the relators.
You're one step ahead of me, or several steps ahead or something. But yes, exactly right. Yeah. So let me sort of explain. Yeah. So the point of this is that we now have a fat graph which is very thin. It just sort of doesn't branch very much. It branches extremely little. And what's the nice thing about that? We have a fat graph that doesn't branch very much. It doesn't contain many paths. If I ask how many paths there are of some length, okay, so the point is, so observe, if y is a thin fat graph, the number of immersed paths in y of length, I don't know, any length L is bounded by, well, we have two choices. We start somewhere, so we have maybe the number of vertices in y for where we start, and then we sort of head off along one of these paths, and every distance capital L we get a choice. So it's something like 2 to the capital L, 2 to the little l divided by capital L. So y is going to be something of order O of n. So when we're comparing it to big collections of words of length order n, this sort of term is kind of irrelevant. Little l is going to be something of size n to some power. Maybe L is going to be something like epsilon n, or a half n, or something like that, 0.3 n. The point is, if L is really, really big, this is much, much smaller than 2k minus 1 to the, I don't know, epsilon n. Well, epsilon is a different epsilon. Epsilon is delta. Okay. So these are the kind of, what we're trying to do is build a fat graph. What would be bad about having our fat graph? We've got this fat graph. What would be bad? One bad thing would be if this fat graph were not pi1 injective. Right? One bad thing would be if there's a loop in this sort of one skeleton of our surface which bounds a disk in the target. For instance, if it was a relator. Well, some of them are actually going to be relators, but we'll get back to that in a second. But if we just sort of pick a random path here, and there aren't that many paths, we going to compare this with paths of length n, and we ask how many we have. We have 2k minus 1 to the delta n of them. We think of our fat graph itself as just a collection of paths in the random model density, where the density is as close to 0 as we like. From the point of view of this model, it's essentially invisible. You just can't hit this fat graph. It's too sparse. It fits through all the cracks. Right? That's the whole point of making a thin fat graph. It's very elusive. Okay, so this is sort of the idea. This is the thin fat graph. So now, how do we build one surface, say in the one relator model? How am I doing for time? 15 minutes? Yeah, okay. So how do we build one surface Well, as Peter says, where are we going to get a couple of random words from? Well, we have one. We've got the relator R. So let's take gamma to be equal to just R. Well, that's no good, because R is not going to be homologically trivial, so that's just silly. So let's take gamma to be R union R inverse. One copy of R, one copy of R inverse. That's better. That will be homologically trivial. So you notice I didn't say in the thin fat graph theorem that the different guys had to be independent of each other. In fact, I didn't mention independence at all. This is the whole point of not mentioning randomness. I just talked about pseudo-randomness. Pseudo-randomness is just a kind of equidistribution on some scale. If I have two things which are pseudo-random, their union is pseudo-random. In fact, the same thing twice is pseudo-random. The same thing 7 times is pseudo-random. So this is sort of pseudo-random, homologically trivial, so it bounds a very thin fat graph. You're looking at me like I'm an idiot, because I mean, it bounds an extremely thin fat graph, namely an annulus. Okay, so this is not the right surface, but at least let's sort of show that morally this is correct, right? Because what can we do? We can cap the top part with R, the disk bounded by R, the bottom part with the disk bounded by R inverse. We have a surface, it maps to our target, and it's pi-1 injective. All right? Well, okay, so that's a first approximation. Let's see if we can do a little bit better. All right, so we want a slightly more complicated surface than this, just for the unbelievers. So what we do is we kind of take. So there's kind of a problem actually, and the problem is I had this argument, heuristic argument, which maybe went by a little bit too quickly, which sort of said that this thin fat graph, from the point of view of the random group, it's sort of invisible. It's very unlikely to be a coincidence between words in this fat graph and the relators in the model. That's true for every relator except the one relator that you use to build this fat graph. This fat graph, whatever it is, it's sort of independent of all the later relators that you throw in after the first one, but it's not independent of R. It's been built from R in an extremely explicit way, actually. It's not independent at all. So you can't just use a probabilistic argument to argue that it's going to be injective, whatever we do in this one relator group. So what you do is you kind of try to separate off the dependence. So we build this kind of thing, which I'm going to call the sort of the bead decomposition. So what I do is I have R here, and I have kind of should be the same number of these. I shouldn't have picked so many. R inverse here. And what I'm going to do is I'm going to try to break R up into a bunch of sort of little regions here of length n to the 1 minus delta, n to the 1 minus delta, n to the 1 minus delta. So you feel as though n to the 1 minus delta is pretty close to n, but on the other hand, there are n to the delta of these beads, and that's a big number. So there's lots of beads. And we want the beads to kind of have to be separated by pairs of words which are mutually inverse. And I want the length of these guys to be some constant c log n. So I've got these words of length n to the 1 minus, these beads of length n to the 1 minus delta, separated by these bottlenecks of size constant log n. You need to choose the constant appropriately, but anyway, you can do it. And you have exactly the same picture down here. And then what you do is you say, well, this bead plus this bead is homologically trivial, because it's the same bead, the bead and its inverse bead. So this bead plus this bead is homologically trivial. So I can fill that in with a thin fat graph, which, if you like, is the spine of a surface. This bead and this bead are homologically trivial. I can fill that in with a thin fat graph, which is the spine of a sort of thin surface. And I do the same thing here and here and here. And I get these bunches of sort of surfaces where each one of these is kind of a thin fat graph in its own right. And they're separated by these bottlenecks. And what do I want to do? I want to show that this resulting surface, so then I cap this off at the end by gluing in one disk at the top to R and another disk down the bottom to R inverse. And now I have a closed surface. It's got two cells, right? And this sort of big trivalent graph is one skeleton. And now that maps to my one related group over here. delta is a number less than 1. A small number less than 1. Okay? And C depends on delta, but it doesn't really matter how. So what's the point here? I want to show this map is injective. How do I show it's injective? Well, I just need to show that every loop in the one skeleton here is essential over here. But what are the relators? Well, the only relator here is R. So this is certainly a small cancellation group if R is big and random. So the only way for a loop to be fail to be, to be normally generated by R, if it's reduced, cyclically reduced, has to have long subwords in common with R or R inverse. Okay, so we look at the paths which are in this piece of fat graph here, and there aren't many of them. Sort of logarithmically speaking, they're almost invisible. So this piece of fat graph here is more or less guaranteed not to have any long paths in common with the parts of R that are outside. So this independence trick, the idea that this fat graph here is unlikely to share long subword in common with other words of length constant n, that holds if you compare this piece of the fat graph with these other sort of pieces over here, the pieces that are on these other parts. See, this piece of fat graph here was built from this part of this relator, but the other parts of the relator are more or less independent. So this fat graph is basically independent of these paths. So there's no long path in this fat graph in common with long path somewhere else. So suppose there is a long path somewhere. So there's going to be a long path somewhere in R. Long path somewhere in R, which also occurs in the fat graph somewhere. So where can it be? It's sort of size constant n. It's a different constant. This long path of size constant n. Where is it going to be? It's got to have a bit of it. Let's say a little bit of it starts over here. So it's a little bit of it in this piece here. Well, this piece here is independent of all the other guys. So whatever this piece is that occurs in this fat graph, it's not going to appear in R or R inverse outside this bead. So this long path, wherever it appears in R or R inverse, it's going to have to appear in the same bead. Okay, so this is a piece of this path that we're tracking. We're tracking it in the fat graph, and we're going to track it in R. It has to sort of appear basically in the same bead. Yeah.
I didn't get the step where you fill in these red.
Okay, well, I have a loop and another loop. You could do that. That wouldn't give you something trivalent, before valent at these points here.
But how are you filling that in?
You fill it in using, there's a relative version of the thin fat graph theorem. Says if we've started to glue a little bit of it and we've got a little bit of fat graph, we can extend that to a fat graph such it's still cyclically reduced. Yeah, you fill it up not in the most stupid way. Any other way is fine somehow. Yeah.
But that's sort of relevant to
yes, it's relevant, but it's yes, but just so there's sort of a if you like, I'm about to glue this up to something. What I glue it up to is something here instead of, and then once I've done that, I keep going, and then So I've got a little bit of this path. It's in here, but eventually has to leave this path. Eventually has to leave this because this guy has to leave. When this guy leaves, it goes over to the next guy. This long segment of R can't have anything long in common with anything in this bead. So what that says is that if we're tracking this word, we've got two copies of this word, one in the boundary, one in the one skeleton. If we're tracking it along, when we hop over to the next guy, we have to hop over to the next guy at almost exactly the same point in time. So we've got a coincidence. When we track it along to the next bead, we have to hop over at the next point. And we have to hop over at the next point. And we get a coincidence. We have a lot of coincidence. We get n to the delta coincidences. Even if delta is small, n to the delta is big, and we're just not going to have that many coincidences. So we're sort of effectively treating a single random relator R as lots of independent random relators for the point of view of this argument. And that's kind of good enough to show that we don't have any compressing disks in this surface. So now we've got one essential surface in our one relator group, and we just throw in all the rest of the relations and check using sort of small cancellation theory as developed by Jan Olivier that the surface persists at, say, is pi1 injective. So happy birthday.
Questions or comments?
Oh, well, the same reason you know it's injective. It's sort of by small cancellation theory, right? I mean, you know, say in this one related group, not only is it nothing, not only does it have no guys of length a half n in common with R, has nothing of size 0.0001 n in common. So it's extremely close to being, you know, completely, yeah. And then the same, there's a sort of estimate. Olivier tells you exactly what the Dane constant, what the delta of hyperbolicity constant is at density d, and using that, showing that you have no cancellation on a certain scale, shows by the usual way that you're 1 plus epsilon quasi, or k quasi-geodesic, but then you can just check that k can be taken to be 1 plus epsilon. Yeah.
Do you expect every or many finitely presented groups to appear with overwhelming probability?
Yeah, so you can soup this thing up a bit. You can certainly, instead of putting a surface in here, you could produce, and Ian was sort of talking to me about this on Wednesday. You can take say a surface with boundary, and then you can have the boundary wrap 7 times around a loop, right? So you can build something of the form product of commutators is a 7th power. So what you get then is sort of some guy which has some z mod 7 torsion in it. And then actually there's a nice application that Ian pointed out, is that you could take that sort of free product something, some F2, and if the density is lower than a 6th, you know this guy is a virtual retract. And so actually you get exponentially growing z mod 7 torsion for every value of 7 or something. So there are other things you can do. You can build these sort of, what are they called, omega residually finite limit towers of lots of different kind of combinatorial types.
Contains some sort of universal curve.
Yeah.
So maybe the group contains every.
Yeah, it doesn't contain every surface group, right? It doesn't contain a surface of genus 2. But it sort of contains every topological type. Yeah, so Henry Wilton and I are sort of writing something at the moment. If you pick one of these towers, you take sort of something like a surface, you know, with free group, attach a bunch of surfaces, attach a bunch of surfaces. If you tell me the topological kind of type of that tree or something, you can build guys of that kind, and you can, yeah. So it sort of has all combinatorial types, yeah.
Questions?
Yes?
Are there other nice threshold situations for a group property that changes drastically at one surfacing?
Well, yes, in fact. I mean, there are theorems to the effect that, so theorem of Zook in a certain model, and Katowski in this particular model says that above a third, a random probability of third, the random group has property T. So, and then below a 6th, why as Olivier show it's cubulated, and therefore by Ian is virtually special. So there's sort of, yeah, interesting kind of properties there. They're kind of in the mix. Yeah. So one thing I mean, I'm a little bit surprised no one asked, maybe no one really cares, whether the argument could be used to attack sort of all hyperbolic groups, one-ended hyperbolic groups. So I mean, one thing I will say is that I think is sort of maybe what the argument gives you, I think, is a method to produce interesting maps of surfaces to arbitrary one-ended hyperbolic groups. Maps which are not obviously compressible and which I think have a good chance of being incompressible. Showing that they're incompressible in general would be much harder, but the constructive aspect of the proof is very flexible. You need to sort of replace randomness in the generators with another kind of randomness in the group, like, you know, horocycle flow or something. But anyway.
So this looks very different from what I understand about the von Markovich construction. I mean, philosophically, do they have any?
Philosophically, I think we owe them a big debt, because in 2 places, actually. So one place, just the whole idea of using kind of probabilistic methods, you know, to generate the pieces from which you're going to build a surface. Philosophically, I think that's a fantastic idea whose potential has not been scratched yet. Second of all, there's another sort of cute, subtle point. In the proof of the thin fat graph theorem, there's sort of a couple of steps, and one of the steps involves doing a kind of gluing up an almost equidistributed collection of pieces, which is very similar actually to their, again, morally similar to their proof of the Ehrenpreis conjecture rather than the surface subgroup conjecture. And the point being that if you have an almost equidistributed collection of pieces, what's really nice about that is that you can sort of pretend that you can act as though you had positive and negative combinations of pieces. There's this sort of principle that we call it, this is the Dirac pants C, or the Dirac, pieces, fat graph C or something. You've got this collection of pieces, and their difference from being equidistributed, you can treat a whole as sort of a negative copy. So you can sort of take things away. You can do kind of a gluing thing where you can glue something to something, and then you get relations, and then you can act as though you're in an abelian group. When in general, if you're gluing things together, you have to kind of, usually you think you're in a semi-group because you can't glue -3 copies of something. So there's sort of a principle there that we use. So, yes. Yeah.
Do you think there might be like a random model for higher dimensional hyperbolic groups, like random simplicial complexes that this technique might work?
Well, first one would need to have a good model before one asks whether the method works. But yeah, as you could certainly start with a high-dimensional random group and then throw in relations at some density, and then this will give you surface groups in that up to some density. As I say, I think there's sort of need to worry near the threshold precisely, especially when there's torsion because of this phenomena that Olivier uncovered. But at some density, yeah. But there somehow the high dimensionality you sort of started with it, and then you'd like to generate high dimensional stuff randomly, and that'd be a great thing to do. But I don't know how to do it.
So the question would be, how do you define what you mean by a high-dimensional random group, or a
Yeah.
random high-dimensional group?
A lot of good questions.